Welcome everybody to this video for Algebra 2 Unit 9. In a moment you'll actually see a video I made a few years ago before we switched curriculums this year. During this switch, we decided to keep most of this unit for probability and statistics, but renumbered this unit and a lot of the sections in it. And we also decided to slightly change the layout of things as we did it to make it more similar to the rest of this new curriculum. And because of that, you're actually going to notice that during this video, some of the formatting and layout of things is going to be different than the formatting and layouting of things in your notes, once again compared to the video you're about to watch. But with all that said, the definitions and examples will be the exact same and in the same order and everything, all the same numbers, same wording of everything in both the video and your notes that you have in front of you. So don't worry about that. I just wanted to give you a heads up so that way you weren't caught off guard or anything and that you thought you weren't watching the wrong video and getting the wrong notes. And with that, enjoy the notes. Welcome everybody to Algebra 2, Unit 9, Section 6, Independent and Dependent Events. So page 15 of the notes are going to be over independent events, and then page 16 are going to be over dependent events. So independent is if the occurrence, just one R, sorry, the occurrence of one event has no effect, I'll underline that, it's pretty important, no effect on the occurrence of another. It's like saying, what's the probability of it raining today? And what's the probability of it, I don't know, and what's the probability that if I flip a coin to get heads? Those two events are not related at all. Whether it rains today has no impact on whether or not the coin I flip is heads, and whatever way the coin comes up has no impact on whether it'll rain today. So how you would find the probability of that is to say the probability of A and B occurring is the probability of A just times the probability of B. You just multiply them together. So if you're given, on example 1 here, that events A and B are independent, find the probability of A and B occurring on 1A. So we're told probability of the first event, 0.7, probability of the second event, 0.36. All you do is multiply them together, 0.7 times 0.36, and you get 0.252, aka 25.2%. On the second one, we're trying to figure out what's the probability of just event A occurring if we know the probability of event B and them occurring independently of each other. So we would say, okay, well, we would have done X, whatever probability of event A would be, times 4 over 5, and we get 1 over 4. So we just fill in X for probability of A here and solve it as if we would any other M. And just now, solve for X. So you have to get rid of 4/5. So you would divide, but we don't like double-decker fractions, so you would multiply by the reciprocal instead. So you multiply by 5 over 4. You get X, aka whatever the probability of A is, equal to 5 over 16. And if you wanted to check your work, you'd multiply 5/16 with 4/5, and you should get 1/4. Example 2, in a survey at a football game, 50 of 75 male fans and 40 of 50 female fans said they favor the new team mascot. If one male and one female fan are randomly selected, what's the probability that both favor the new mascot? So, the question becomes, hey, is this independent or dependent? Well, if they're asked, was what the male says going to impact what the female says? And no, they shouldn't, as long as they already were surveyed beforehand. So they were already given their answer, so there's no way that they're going to answer based upon another. And whether you select a male randomly that favors or doesn't favor the female fan has the whether the female fan favors or doesn't favor has no impact on that. So here we say, okay, we do the probability that the male and the female favor it. So you do the probability of the male, which is 50 over 75, times the probability of the female favoring it. 40 out of 50 of them do in this survey. So you can reduce and multiply together. So I'm going to reduce 50 and 50 to 1 and 1. And 40 and 75 I'm going to reduce to 8, reducing by 5 there. And 75 reduced to 15. So we get 8 out of 15. So the probability that both favor the new mascot, if you randomly select a male and a female, is 8 out of 15. Example 3. A survey found that 46% of parents surveyed said that they read to their children at least once a week. If 3 parents are selected at random, what's the probability that all 3 will say they read to their children at least once a week? So a probability that the first parent reads, the second parent reads, and the third parent reads would be equal to the probability that each parent reads. So 46% for the first one, for the second one, and for the third one independently. Because whether or not one parent reads in the survey to their children has no impact on whether another parent does. So you just multiply those together, and you end up getting 9.7%. It would be 0.097 in decimals. So not a very high likelihood that 3 parents selected would all read to their children. Example 4, a 2020 survey found that 42% of high school seniors reported vaping at least one time in their life. If 5 high school seniors are selected at random, what's the probability that all 5 will say they have not vaped at least one time in their life? So 5 different seniors, and the probability they don't vape would be 58%. Well, how do we find that 58%? If you're wondering, you take 100% for all the students, subtract the 42 that said they have once in their life to get 58. And you take that 58 and you multiply 5 of them together, because there were 5 different students. So 0.58 times 0.58 times 0.58. I think I missed one, times 0.58 if I did. And you end up getting what really is 0.58 to the 5th power, if you want to call it that, because it's 5 of them multiplying together. And that would be approximately 6.6%. All 5 seniors randomly selected would have never vaped in their life. On to dependent events. So dependent events are the exact opposite of independent. It's if the occurrence of one event affects the occurrence of another. So this would be like drawing cards from a deck is a very common example for this. So you draw a card from a deck and then you don't put it back. Well, there's obviously going to be less cards in the deck, which will impact the likelihood of what you got. Like say, probability that you draw a red card and then the second one you draw is a black card. Well, it's obviously a higher likelihood that second draw is going to be a black card than it would have been before, because there's one red card missing. So there's a slightly higher than 50% likelihood that the second card will be black, because there's more black cards than red cards at that point. So mathematically what you do is you say the probability of A and B is the probability of event A occurring times the probability of event B occurring given A already happened. So using that given probability that we did last section in section 5. So in example 5 here, you randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is a heart and the second is a club? And we're doing 5A for if you replace the first card before selecting the second, and part B, that you don't replace it. So in 5A, we're saying the probability that the first card is a heart and the second heart is a club. So the probability that the first card is a heart is 13 out of 52. And then you would draw that heart, put it back in the deck. So there's still 52 cards in the deck when you go to draw the second one. The probability that out of those 52 cards, one of them's a club is 13. So you would just multiply these together and get 1 over 16. These you would simplify, by the way. Each of these would simplify to 1/4 in case you're curious, because a fourth of the deck is each suit. And that would be in decimals in case you're curious, 0.0625, aka 6.25%. So depending on how you want your answer, if you want it in fractions, in decimals, or even if you want it as percent, 6.25%. So depending on how you're asked for an answer, how you would prefer answering. I'm good with any of them unless I state otherwise. Now 5B is going to be a dependent event. So 5A was independent. Whether or not whenever you drew the first card, whatever the first card was, I should say, had no impact on the second card because it was put back. Whereas on part B, after you draw the first card, it's taken out of the deck, and then you draw the next. So the probability that the first card's a heart is still 13 out of 52, which reduces to 1 over 4. The probability that the second card is a club, though, there's still 13 clubs in the deck if the first card was a heart. Now there's only 51 cards left. So you would still reduce the 13 and 52 to 1 and 4, but you can't reduce 13 and 51. So you end up just getting 13 over 204, which is going to be quite a bit smaller, or excuse me, not quite a bit smaller, which will be near the same, but still slightly different than part A. So that would be approximately 0.0637, which is approximately 6.37%. So you can see, actually, I said smaller, I misspoke. It's slightly more likely that the second one happens because the first draw doesn't change, but the second draw, you have a slightly, just very small, increased chance of drawing a club if there's 51 cards in the deck and 13 of them are clubs, compared to if there's 52 cards in the deck and one of them is a club. And the more you keep drawing, and as long as the number of clubs stay consistent, the greater the chances we'll end up getting. Example 6. I want you to try this. These two examples for A and B on your own. So the probability of drawing the given cards from the standard deck of 52 cards, first with replacement and then without replacement. So A, probability that you draw a queen, then a jack. So if you replace it, the probability of getting a queen, there's 4 out of 52 of them. The jack, you put it back, you put the queen back, there's still 4 out of the 52 cards. Reducing 4 and 52 to 1 and 13. So you end up getting 1 out of 169. Which, once again, you can leave like that or put in a decimal or a percent. Part B, probability that you get a queen and jack, but you're not replacing it this time. So you draw a queen, 4 out of 52, aka 1 out of 13. You take that queen out of the deck. There's still 4 jacks, but now there's only 51 cards. So this reduces to 1 and 13. And we end up getting it to be 4 out of 663. Now it's kind of hard to tell, like, what are those comparatively. So that's why sometimes you might want to put it in percents or decimals. So percentage-wise, this would be approximately 5.92%, or this would be approximately 6.03%, in case you're curious. So what's the probability on 6 part 2 that you get a jack, then another jack, then a 2? So with replacement, probability of getting a jack, 2. Probability of getting a jack the first time, 4 out of 52. Second time, 4 out of 52 again, because you just put the jack back. And then a 2, 4 out of 52. So you just multiply it times itself 3 times. And you end up getting, reducing all these to 1 over 13, 1 over 13 cubed, which is 1 over 2,197. That'd be approximately 0.455%. Not very likely, in case you're wondering. Now, the probability that if you take the cards out, that you get a jack, another jack, and a 2, well, the first jack, 4 out of 52, the second jack, there's only 3 more jacks in the deck, and there's 51 cards. And then the 2, there's still 4 2s, but there's only 50 cards in the deck now. Hope I put equals for those, but I meant to put times. Let me fix that real quick. All right, so the 4 out of 52 still reduces to 1 over 13. The 3 over 51 reduces to 1 over 17. Kind of do some thinking there for a moment, some mental math. And then the 4 out of, oh my goodness, I wrote 52 on the last one, but I said it correct by saying 4 out of 50 because you took 2 cards out of the deck, both jacks, or 2 of the jacks you've drawn. 4 out of 50 reduces to 2 over 25, and that's all the reducing we can do. So that would end up being 2 on the top, and then 13 times 17 times 25 ends up being 5,525. That is approximately, this is a very, very small one in case you're wondering, 0.362%. Not likely at all. All right, example 7, A and B, and then we're done with the notes for today and for this unit. So you have a key ring with 7 different keys. You're attempting to unlock a door in the dark, so you try the keys one at a time and keep track of which ones you try. That way you aren't trying the same key twice, essentially, is what it's saying. So find the probability that the third key you try is the right one. So that means the probability that the first one's wrong, the second one's wrong, and the third one's right. So the probability that the first one's wrong, well, 6 out of 7 keys are going to be wrong, because only 1 out of 7 works. The probability that the second one's wrong, 5 keys that are still wrong, and 6 keys left to try. And the probability that the third one's right, well, you only have 5 keys left, and 1 of them's right. So we can reduce here, 6 and 6 reduce, 5 and 5 reduce, so 1 and 7, meaning if you do this 7 times, then 1 time that you should get the right key on the third try. Now find the probability that one of the first keys you try is the right one, aka it could be the first key, it could be the second key, or like we just saw, it could be the third key. So you get it within at least 3 attempts, is what it's saying. So what you have to do is you first find the probability of each one of these individually. So the probability that you find it on the third one, or the probability that, let's say, you find it on the second one. The second key is the right key. Or the probability that the first key is the right key. And then you'd add them all up because they're ORs. So the probability that the third one's the right key, we already found that one to be 1 over 7. The probability the second one's the right key, so you'd have 1 out of 7, or sorry, 6 out of 7 for getting the wrong key, like we saw a bit ago. The right key on that one, there's 1 right key, 6 keys left to try, and the wrong key, well, 5 wrong keys out of 5 keys, aka you're multiplying by 1, so you don't even need to write that part really. And the last part, the probability the first key is the right one. Well, 1 right key out of 7 keys, and then 6 wrong keys out of 6 wrong keys, and 5 wrong keys out of 5 wrong keys, which you wouldn't bother trying. And mathematically that shows because, once again, 6 divided by 6 and 5 divided by 5 are just 1. So it wouldn't change the probability of this at all because you're multiplying by 1. So the probability of the second one, that you get the key right the second time, 6 and 6 reduce, 5 and 5 reduce, and you get 1 out of 7. Well, probability that the first one's right. Well, 6 and 6, 5 and 5 reduce to 1 and 1 like we were talking about. So you end up getting 1 out of 7. And then you add all these up. So 1 out of 7 plus 1 out of 7 plus 1 out of 7, 3 out of 7. So meaning, if you try 3 keys, or excuse me, that means 3 out of 7 times, you should get the key right by randomly guessing in the dark 3 out of 7 times. You should get the key right the first 3 attempts, I should say, 3 out of 7 times. All right, that is it today for section 9.6.